Okay, so we're talking about gradient-based methods, and we talked about how the gradient is kind of the like the vector generalization of a derivative, and the Hessian is the vector generalization or matrix generalization of the second derivative. Okay, and so we are going to use that in a computational algorithm for optimization. Okay, and there are many algorithms for optimization. And so but this one we're going to cover today is gradient descent. Okay, and so basically, with gradient descent, let's say you're trying to optimize some function of x, okay? And so, and by optimize we mean minimize in this case. Just pull up my notes. Okay, and so what we do for each step of x, for each step in our algorithm, we start off with some value x, and then we take a step in the direction of the gradient, okay? So, if we have, so we're going to say we have x at time t, okay? And what we're going to do is we're going to subtract off, I'm going to put in an alpha here, and we're going to multiply this by the gradient of x at time t. Okay, and the resulting value is going to be x at time t plus 1. Okay, this so this is the gradient, and this thing alpha, this is called the learning rate. Okay, and this is our current value of x. And this will be the next value of x. Okay, and this is basically the algorithm. You just initialize x, calculate the gradient, and take steps in this thing. Okay, so just I guess the algorithm. Pick an initial x. Okay, obviously find the gradient, take a step to get x at time t plus 1, okay, and then repeat. Repeat until basically the gradient is equal to 0, or the difference between x and x at t plus 1 is really tiny. Okay? Yeah?
For the xt, does that say constant or current?
Current.
Okay.
Sorry. Current value of x. Okay? Repeat until the gradient is 0, or the difference. I should say the difference between the function at x at time t and the function at x at time t plus 1 is below some tolerance level. Give me a second here. Okay, question.
So how do you find like
Yeah, that's a good point. Okay, so we'll talk about all of this in a moment here. Okay, so let me just kind of illustrate how this would work for a one-dimensional thing, and then we'll generalize it to a kind of like we'll do a two-dimensional example on linear regression, which is already solved and simple, but kind of illustrates what we're trying to do. Okay. So this is the gradient descent algorithm for optimization. Okay, do you guys have all of this down? Okay, so so basically for a one-dimensional problem, okay, let's say we've got some function of x that looks like this. Okay, so this is x, and this will be f of x. Okay, and so let's say we start right here. Okay, so basically the gradient here would just be our derivative, right? And so we said, so if this, let's say this is x at time t, okay, and we said x at time t plus 1 is going to be equal to x at time t minus alpha times, and in this case the gradient will be the derivative of our function, right? This is essentially the derivative of f at x at time t. Okay, so let's look at what our derivative is. If I can draw. Okay, so we see our derivative has a positive slope, right? So this thing has a positive slope at x of t. Okay, and so when we find x at time t plus 1, it's going to be our current value of x of t. And we're going to subtract off, oh, I guess I should say alpha is always positive. Greater than 0, okay? So, so you know, we're going to be subtracting off some kind of a positive quantity, right? So alpha times a positive quantity, this is going to be a positive quantity. Okay? And then so our next step, you know, let's say we take a step, maybe this is going to end up being x at time t plus 1. Okay, so we take a step and we end up here. Okay, so we're at x at time t, and then so this is this quantity that we've moved. This is alpha times our slope. Okay, and so this is now x at time t plus 1. Okay. And then at this point we see we got the same kind of thing going on. We've got a positive slope, okay, but the slope is much smaller this time, okay. And so at x, if I'm at x at t plus 1, then the next place will be x at time t plus 2, okay. I'm subtracting off alpha times, you know, we still have a positive slope here. But this positive slope is, you know, a smaller slope. Okay, so the next step that we take will be a little bit smaller still, okay? And so the next step will be a little bit smaller, and this will be x at time t plus 2. Okay, and this algorithm continues, and you know, our slope is getting smaller and smaller, and so our steps get smaller and smaller and smaller until we reach the minimum. Okay, and eventually we reach the minimum. Okay, and so the slope basically tells us, you know, are we is the function increasing or decreasing at that point, and we move in the opposite direction, right? So we're moving in the direction of descent. Okay? And then as we get closer and closer to the minimum, this derivative gets smaller and smaller, so we don't have to really adjust alpha. The steps just get smaller on their own because the derivative or the gradient will be shrinking, okay? And eventually we get to a point where it stops, okay? And then, you know, let's say, so well, I just want to, maybe I'll pause and just make sure this is okay with everybody. Okay? And then, you know, let's say we were on the other side of the graph, okay? Let's say our initial starting point was over here, okay? Okay, so here, you know, if this is x at time t, x at time t plus 1 is x at time t minus, we still stick with alpha, the derivative of f of x at time t. Okay, this thing, we see this thing, we have a negative slope, okay? It's so hard to draw. Okay, so we have a negative slope. Okay, and so, you know, when we subtract off a negative, we're going to be adding a positive quantity. So it'll be x of time t minus a negative quantity. Okay, so our next spot at time t plus 1 will get us, we'll move in this direction. Okay, so our next spot is going to be right there. Okay, so this would be the gradient descent algorithm if we were dealing with a one-dimensional thing. Okay. Okay. You know, we had some question about, you know, how do we pick alpha? All right, and that's a hard question. We don't. There's no simple answer that says this is the best alpha to use. Okay. So a lot of times it's a little bit of trial and error. Okay. If I may go to the next slide. Okay, so picking your learning rate alpha. Okay, and some texts might use the learning rate lambda. Okay. Okay, so picking your learning rate alpha. Okay, so if your alpha is too small, you are basically, you're taking tiny baby steps, okay? Okay, and convergence will be slow. So basically you're just moving from here to here to here to here to here. You know, you're gonna have to take hundreds of steps just to go down the thing. Okay. On the other hand, if alpha is too large, okay, you can quote overshoot the minimum and end up diverging. Yeah.
So maybe not in like one-dimensional data, but higher. Is there problems with like the time it takes for the gradient descent?
Actually, gradient descent is a very efficient algorithm for high-dimensional data. Okay, whoops. I'll talk about it. So let me just show you what could happen if your alpha is too big. Okay, so if your alpha is too big, and let's say you start here, okay, and you take a huge step, and you end up over here for the next spot. Okay. Well, then it says you should go back this way, but notice this is even steeper than this point, okay? And so if your alpha is too big, then it's going to say take an even bigger step because your step was even bigger. And so now we're even at a steeper point, and we end up getting a diverging thing, okay? Because, you know, our alpha is too big. So this is problematic, okay? Okay. And then a note about gradient descent is that gradient descent will get trapped at local minimum. So, you know, if you have a curve like this, okay, and you start over here, it's gonna move down, and it's gonna stop there. Okay. Yes. Question. So to find the maximum, do gradient descent, still do gradient descent, just put a negative sign on your function. Okay? So you just, if you're looking for the top of the hill, just flip it over. We can do that in math, and then do the gradient descent. Okay? Okay, and then so gradient descent will get stuck at local minima. No, I mean just the base algorithm of gradient descent, you're going to get stuck at local minima. So a lot of times people recommend having multiple starting points, okay, and just to see where things go, okay. So have multiple starting points because, you know, if you start over here, then you'll find this one, okay? And so if you have multiple starting points, you might end up with different, it'll converge in different locations, and then you can compare the values at those different places. Okay, so this is, that's gradient descent, just kind of what we're doing in one dimension, okay? And so if we, if we're dealing in 2 dimensions, okay? So let's say we've got x1 and x2, and we have, I don't know, some function that, how do I draw this? Okay, so just imagine we've got some kind of, yeah, I don't know. This is supposed to look like a bowl, okay? Okay. All right, so you know we've got some kind of function of 2 dimensions here, x1 and x2. So you know, let me just turn this into a contour plot. So we've got x1 and x2, okay? Okay, so the gradient we know is tangent to our contour lines, right? So it shows us, okay, so the gradient of f is not tangent, it's orthogonal to our contour lines, okay, and it basically shows the direction of steepest ascent or descent, So I guess actually the gradient is points in this direction, and then we would be going in the negative direction, okay? And so basically, you know, we take a step, and then we find the gradient at this point. We take another step, we find the gradient at that point. We take another step, and you know, we find the gradient at each of these points, and we end up making it to the minimum. Okay, and it works. You know, we can have n-dimensional data, and this gradient descent works because the gradient is our vector generalization of the derivative. Okay, so the same concepts work. Okay, and the gradient descent is actually pretty efficient for high-dimensional data. Okay. All right, so, you know, how would we actually go about implementing something like this in a computer program? Okay. So for this example, well, we'll see if we have time. We might run out of time to get the whole thing working today, but we'll do a simple example by hand, and then I'll kind of write some pseudocode showing how this would be programmed, and then we can go about actually putting it into R or something like that. Okay, so what we're going to try to do is we're going to use gradient descent to find the best fit line for the following data. Okay, so I have X, and I've got Y, and I got 1, 2, 3, 4, and this will be 2, 6, 4, 8, okay? Okay, and there, you know, what is kind of the best fit line? Something like this, all right? Okay, so we have to define basically a loss function, and for linear regression, so the loss function is also kind of known as like how we're measuring how good or bad the fit is, okay? So the loss function is how we will measure how good or bad our line of fit is. Okay. Okay. And so here we will define our loss function as the sum of squares residuals. Okay, and so in our case, our loss function okay, it is our loss function is a function of the parameters that we choose for our line of fit. Okay. Okay, and so, you know, our line of fit has two parameters. Okay, basically an intercept and a slope. Okay, so we'll use our traditional notation of B0 and B1. Okay, and so our choice of the intercept and a slope will change, the line that we use. Okay, so is that the good line, or is this the line that we want? Which line is best? Okay, so each of these will have a different slope and a different intercept. Okay, and basically our loss function is calculated is going to be equal, so our total sum of squares residuals is equal to the sum of each data point y minus ry hat at that point. All right? And okay, so this becomes, so our line of fit, we say y hat sub I is going to be B0 plus B1 times x sub I. Okay, so this is going to be yi minus the quantity B0 plus B1 x sub I squared. Okay, so far so good? All right, so I'm going to copy this over. So this is the function that we are trying to minimize, just to remind us, okay? So we want to minimize this function, okay? And so this is a function of two parameters, B0 and B1, okay? So effectively, you can think of this as B0 and B1, and we've got some kind of three-dimensional thing going on here. Okay, and we're trying to minimize this two-dimensional function of B0 and B1. Okay, the yi's and xi's, those are defined in our data. Okay, so our function is not, we are not adjusting yi or xi, they are fixed as part of our data. And what we are adjusting is the B0 and B1x. Okay, so to implement this algorithm, we would have to find the gradient of our function here. Okay, so let's see, how do I want to do this? Okay. Okay, so what we're going to do is we're going to find the gradient of f, okay, and our f is a function of b0 and b1, right? So we're going to have to find the partial with respect to b0, and then the partial with respect to b1. Okay, so the partial with respect to b0 is what is this? I wrote this, I did the math ahead of time just because I know when I have to do derivatives on the spot, it's always bad news. Okay, so this is going to be, the square term comes down, and it's still going to be the sum. Because we've got a minus term, it's going to be minus of the y sub I minus quantity B0 plus B1 x sub I. Okay, I think I did my math correctly there. Right, just chain rule it, right? Okay, and then for the first derivative, for b1, so partial with respect to b1, I'm going to sum this, and so with chain rule we get a negative x sub I out here times y sub I minus b0 plus b1 x sub I. Okay. All right. I think my math is correct. All right, and then so just to reiterate, our data is 1, 2, 3, 4, and we have 2, 6, 4, 8. Okay, so it's actually this thing, the full gradient with respect to b0 is going to be 2 times the sum of minus. I would have to do every single one of these points. It would be 2 minus b0 plus b1 times 1 plus the next one, which is going to be 6 minus the point b0 plus b1 times 2 plus etc., etc., etc. Okay, I would have to do this for all 4 points. Okay, so here, it's still so basically once we plug in our x's and y's, the actual values from our data, we see that it's truly just a function of b0 and b1, right? Okay, and then the same is true for the gradient for with respect to or the the component of the gradient with respect to b1. Okay, so this is once you plug in the values of x and y, it is just a function of b0 and b1. Okay, so let's shall we try to program this? Okay, let's see if we can do this. I'm nervous. We're going to be coding in real time here, which is always always risky. What's going on here? Why is this not working? Okay, so let's go. So we're going to start off with we're going to define kind of our error. We're going to just say this is equal to 0. And then, so we should say, we'll create our matrix. We'll call this points. There's going to be a matrix. And what we have is the points 1, 2, 3, 4, 2, 6, 4, 8. Number of columns is 2. Okay, and then names of points is going to be, what's going on there? X and Y. So let me just make sure this is entering here. What happened here? Column names? I need to do column names. Okay, so let me get rid of okay, that's what I want. So I can do points 1 comma x, and then yeah, okay, good. All right, okay, and then so we're going to define a function called the error. Wait. Total error is going to be a function of basically our points matrix and our values b0 and b1. Okay, and this is going to be, we're going to take our point, so let's see. This is probably not the efficient way to go, but we'll just say for I in 1 through dimension of points, and we want the number of rows, then what we do is we're going to take so I'm going to have to, here, let me just slide this over. This is too cramped for me. Okay. So what we want to do is we take our error, and we're going to add to the current error the difference between points I comma y minus the quantity. And then what is this? This is our slope, so our intercept b0 plus b1 times points at I comma x, right? Okay, and then we're going to take that and we're going to square that difference there. Okay, and then return back the error after all of this. Okay, so let's we'll try our function out, and we'll just say total error of points using 0, 0, and it says our total error is 120. What happens if I throw in the slope 2? Okay, that reduces it, and I know my answer is something like, or actually I don't know what it is. Okay, but that seems to be working, right? Because if I, the manual check of our data, 1, 2, so if y hat is equal to 2x, which is basically what this is, 0, intercept 0 plus 2x, our y hats would be 2, 4, 6, and 8, and our error would be 0, 2 squared, and 0, so our total error is indeed 8, so that seems to be correct. So far so good? Okay, so we want to minimize this, so we're going to have to create our gradients. Okay, so I'm going to have b0 underscore gradient. And how do I do this? Okay, so this is going to be again a function of our points and our choice of b0 and b1. Okay, and okay, so our gradient, we found the gradient of b0 to be this thing. So how do I get that into R? Okay, so I want I'm going to say so I'll start off with a okay, so we'll just call this the gradient. We're going to start that off equal to 0. This is not the most efficient way to go about it, but we'll just do it this way. Okay, so for I in 1 through the number of points that we have, dimension of points, what will we do? We're going to take minus 1 times, we want our y sub I, so points at I of y minus, I'm sorry, this should be negative 2 because of the 2 out in the front, minus the quantity b0 plus b1 times points at I comma x. So basically our x of I. Okay? And so what we will do is we're going to start off with a gradient, and we're going to say update our gradient, so we take our gradient plus that thing. Okay, and then return the gradient. Does that seem reasonable? I hope I'm programming this correctly. Okay, and then I think our B1 gradient is quite similar, except our B1 gradient, what does that thing look like? That thing looks like this. So let me just slide this over. Okay, so I want our gradient plus negative 2 times our x sub I. So points at x sub I, so I comma x times everything in this thing, points minus that. Okay, so I think the gradient with respect to B1 looks like this. Okay, so we have our two gradient functions. Okay, and then no, we're going to run out of time here. So with each iteration, what we want to do is, we start off with an initial. I guess we'll start off with B0. We're just going to set it equal to that, and then we'll do that. Okay, and then we'll just say we'll just do 3 steps. Okay, for I in 1 to 3, what we're going to do is we're going to start off with our B0 and B1, and what we do is we calculate, we find the B0 gradient of our points and our current estimate of B0 and B1. We find the B1 gradient of that. Okay. And so I'm going to call this B0 step and B1 step. Actually, and then, I'm sorry, I need to set an alpha, right? A step parameter. So I'm just going to use 1 for now. Okay? So this is going to be alpha times our gradient, and this is going to be alpha times that. Okay? So we're going to take our steps, and then after we've calculated the size of our steps, okay, we're going to say the new step, B0, new value of our intercept is going to be our old value minus our step, and then the new value of our slope is going to be B1 minus the step, okay? It's important that you don't directly say the next B0 is going to be, it's important that you don't do update B0 and then update B1, okay? You have to figure out the current step, because if you update one, then, so if I updated B0 here immediately after finding the step, then this gradient is going to be thrown off because now it's plugging in the new value for B0, okay? So you have to take the current values of B0 and B1, find out how much you're going to step in each of those directions, and then after you find out how much you're stepping, then you update that step, okay? So what we can do at each of these points is we can just print out B0 and B1 and just see what happens, okay? So we'll try this out. I hope this works, and we'll see. Oh, did I mess something up? Oh, I didn't enter these things either. Okay, and I know we're just out of time here. Oh, I'm going in the wrong direction here. Okay. Yx B0 B1. Okay. Of course, something isn't working quite right. So let me figure this out. But okay, I'll make the fixes and we'll finish this in on Monday, and then and we'll continue on talking about gradient descent in this context here. Okay, have a great weekend.